I'd like to do example 7.4 out of the text. And show you a little bit with a continuous random variable, and also to rediscuss the normal distribution. So let me go through some facts. An opinion poll asked a simple random sample of 1,500 American adults what they thought the greatest problem was facing our schools. Now, suppose, hypothetically, if we were actually the statistical all-knowing God, we might know that 30% would actually say drugs. We would call that value P, which is the true proportion of people who would say drugs. That's called a population parameter. The guess or the estimate for that population parameter would be P hat. So that's the estimate for P. As we've said before, hats mean guesses. Now, as it turns out, from some reasons that we'll see in Chapter 9 right after the Christmas break, that these answers, the P hats, because if I take different samples, I'll get different responses. So I could get a bunch of different P hats, and it turns out that these P hats follow the normal distribution, the center of which is P, which is 30%, and the standard deviation of which is this. And in Chapter 9, we'll go through exactly why that is. So just accept that for right now. My question is, what's the probability that my poll gives me an answer that's more than 2 percentage points away from the truth? Let me say it again. What's the probability that my poll gets an answer that's more than 2 percentage points away from the truth? In other words, how likely is it that I'll be so unlucky that I'll either get a P hat that's bigger than 0.32, or I'll get a P hat that's less than 0.28 as a result of just being unlucky, because I took a simple random sample, so I don't have sampling bias here. Well, first thing I'm going to do, because I'm a little confused, but I know that drawing a picture is a good idea. And there's a normal curve, and the center of that normal curve, as we just said right here, is 30, and the standard deviation is this. The question we've asked is, what's the probability I get an answer either out here or over here? Now I know that this distribution is going to be symmetric, so this is the same thing as asking for 2 times the probability that I get a P hat less than 0.28. Well, it turns out that if in case you've forgotten, the next thing we're going to do is standardize it. So the P hat becomes a Z, and this becomes the estimate minus the parameter over the standard deviation of the estimate. That gives me a Z-score of negative 1.69. I can then either look up negative 1.69 on my pink chart, or I can type it in my calculator. Typing into the calculator would be normal CDF of a lower bound, comma, upper bound. And either way, I'll get that my probability is this. Now that's the probability that I get something down here, which of course is the same as the probability I get something up here, which is why I'm going to multiply it by 2 to end up with, that's not right, I forgot a 0. Ah. All right, one more try. Get rid of that. Multiplying that by 2. It's 0.0910. There it is. Got it. Now that means I've got roughly a 9% chance that when I take a sample of 1,500 people, and by sample I mean a nice simple random sample, I've got a 9% chance that my random sample will fall either over here or over here, more than 2 percentage points away from the truth. These calculations are very comparable to what we did back in chapter 2, only now I'm using the concepts of probability and of continuous random variables as I discuss it. So this should be somewhat familiar to you, although it may have gotten a little rusty since we haven't used it in a while.